Stephanie Hanson, who will be talking about patterns in crime, one of her favourite topics. She's a well-known alumnus from York and now at Australian National University, and I think I will let her talk through the rest of the speaking.
Hello, yes. So I'm at the Australian National University at the moment. I'm a PhD student of Tim Trudgeon's, and most of the work I do has some relevance to do with patterns in the primes, so I'd like to tell you a little bit about that today. I'm not really going to assume that you have much in the way of knowledge of prime numbers, so, if you're a complete novice to the area, welcome aboard, and I hope that I managed to convert you. So let's start off with what a prime is. So a prime is any number which can only be divided by 1 and itself, and we explicitly forbid 1 from being a prime. And I'll talk a little bit about that in a minute. Euclid, in his Elements, proved that there are infinitely many prime numbers, and a result which is known as the fundamental theorem of arithmetic tells us that every whole number can be written uniquely as the product of prime numbers. So as we see here, 28 is 2 times 2 times 7. And if we were to let 1 be a prime number, then we would lose this uniqueness. So we would have 28 being able to be written in this way, or as 1 times 2 times 2 times 7, or 1 times 1 times 2 times 2 times 7. And this is not a nice thing. We like uniqueness. So this is why 1 isn't a prime, even though in my heart of hearts, I kind of still think it is. But crucially, this means that primes are defined by multiplication. They're a multiplicative object, which means that it's rather silly to ask questions about them which haven't got anything to do with multiplication. But bless us number theorists, we still try. We ask lots of questions to do with addition and prime numbers, and that's what most of the talk is going to be about. Okay, so this is the list of the first 100 primes. And mathematicians for hundreds of years have stared at lists like this and tried to divine some form of pattern, some form of structure to these numbers. And one of the patterns that they think they found is the one highlighted in red here. So as you'll notice, 3 and 5, 11 and 13, 29 and 31, these are all primes which are separated from each other by precisely 2. And a natural question, which we think Euclid asked, is, does this continue on forever? We don't know whether Euclid actually posed this. We think he did, but he never wrote it down anywhere. The first time we see any conjecture which looks remotely like this written down is in 1849 by a mathematician called Alphonse de Polignac. And he actually wrote this down in a significantly more general form. I'll talk about that generalization a little bit later, but for the moment, let's just focus on the twin prime conjecture and see what sort of evidence we've got that this might be true. So we're going to write pi of x as being the number of prime numbers which don't exceed x. So for instance, the prime numbers less than 10 are 2, 3, 5, and 7. There are 4 of them, so pi of 10 is 4. Similarly, pi of 100 is 25, although I'm not going to list all 25 prime numbers less than 100. And we've also got pi 2 of x for the number of twin primes less than x. So again, we have 3 and 5, which are separated from each other by 2, 5 and 7, which are separated from each other by 2. So there are 2 twin primes less than 10. So pi 2 of 10 is 2. And we have 8 twin primes less than 100. Now, one of the most fundamental results in prime number theory is called the prime number theorem, which was first proved by Jacques Hadamard and Charles de la Vallée-Poussin, which I believe literally translates as Charles of the Chick Valley, oddly enough. It was first conjectured by Gauss many years earlier, but he couldn't prove it. And what it says is that the number of primes up to x looks quite a lot like x over log x. So as we get higher and higher up, the number of primes less than or equal to x will look more and more like x over log x, which grows a little bit slower than x. So there are actually quite a lot of primes, but not as many as x. And we have a similar idea for how the number of twin primes should go. and it should actually look like some constant times x over log x squared as we get closer and closer to infinity. And we know what that constant should be. It should be about 1.32. And let's see a quick plot of that. So this is actually the number of twin primes divided by x over log x squared divided by 2 for some reason. There are important reasons behind this, but let's ignore them for the minute. And we can see that, okay, yeah, it does look like it's going to something. It might not be the number we want to. So the constant that we expected to get to is the blue line at the top. Yes, there's some strong evidence that this might be true, some numerical evidence. But really, who knows? Let's look at some more numerical evidence. So we're going to consider the series a half plus a third plus a fifth plus a seventh plus an 11th plus a 13th. So the sum of 1 on a prime. And how does this behave? Well, we know that this grows like double log x, or more importantly, that the sum is actually divergent, that it heads off towards infinity. But if we were to consider the sum of the twin primes, that actually doesn't go off to infinity. So looking at a third plus a fifth plus a seventh plus an 11th plus a 13th and so on, that will go to some finite number, which it will never exceed. We actually have a rough idea of what that number should be. It's about 1.9. And this tells us that it doesn't tell us whether there are infinitely many or finitely many prime numbers, but it does tell us that there are significantly fewer twin primes than normal primes. So that's kind of interesting. The date of this theorem is also a little bit odd. So Viggo Brunn, he was a mathematician who worked at Göttingen in Germany from about 1910 to 1922. And this result was based significantly off an earlier result in 1915 that he proved. He proved a result called Brunn's pure sieve. And this is a deep result in sieve theory, which I'm very interested in, and more importantly, in prime number theory, which at the time had no practical applications whatsoever. This was years before mathematicians were involved in cryptography. And this was during World War I. And that's kind of neat to me, that even in the midst of total war, that Germany was still investing in pure research. Okay, so let's look at the gaps between primes. So another way of writing the prime number theorem is that if we say that Pn is the nth prime number, so P1 would be 2, P2 would be 3, P3 would be 5, and so on, then the nth prime will look roughly like n times log n. And what does this mean? Well, if we look at the gaps between consecutive primes, so that's the difference between the nth prime and the nth plus 1th prime, then that'll look like n plus 1 times log of n plus 1 minus n log n, just by substituting in. And log of n plus 1 looks a hell of a lot like log n. We get a little bit of an error term thrown in, but that's small. We can make this mathematically rigorous. We're not just throwing away stuff for the sake of it. So we get this expression here. And then we can just do normal subtraction to get log n. So the average gap between prime numbers will be about log n. So that allows us to make sense of the following theorem. Let's ignore the limit for the moment. So Pn minus 1 over log n, because log n is the average gap between primes, this whole thing should be about 1. Now limit here means it looks at the smallest value that keeps showing up. So for instance, if we were looking at the limit of the sequence 1, 2, 1, 3, 1, 4, 1, 5, 1, and so on, the limit would be 1 because 1 is the smallest value that keeps showing up. Whereas if we were to look at the sequence, the limit of 1, 2, 3, 4, 5, and so on, the limit, there wouldn't be 1, so it would be infinity. But here, the smallest value that keeps showing up between the quotient of the gap between consecutive primes and the average gap is 0. And this tells us that infinitely often primes are a lot closer to each other than we expect, than they are on average. They're multiplicatively as close as you want. So that was proved back in 2006. The twin prime conjecture would imply this, but it doesn't go the other way around. Then in 2013, a mathematician called Yitang Zhang proved that there are infinitely many prime numbers which differ by less than or equal to 70 million. Now, Yitang Zhang was a mathematician at the University of New Hampshire. It still is, I think. He was a massive unknown when he released this result. He was in his 50s. He graduated from doing his PhD, and by all accounts, he was a great PhD student, but he couldn't find a job anywhere. And so he worked for years. I think he worked at Subway. He worked as an accountant. He didn't really have anything mathematical going on. He managed to find a job a few years ago at the University of New Hampshire, and then released this massive game-changing result, which spurred the entire mathematical community to work on it. But so this result, in the language above, we can write it as this, which, yeah, it's just the same thing again. But so this spurred the mathematical community on to try and reduce this bound, because 70 million is a big number. It's a lot smaller than infinity, but it's still a very big number. And there are a few initial drops in the bound. I think it came down to about 59 million in the first couple of weeks, but then a polymath project started, which is essentially a massively collaborative mathematical research project. This one in particular was headed by Terry Tao. I think the first polymath project was the brainchild of Tim Gowers, but Terry Tao did this one because this is also very much his area. And they caused the bound to start tumbling down and tumbling down. There's a blog where they actually kept the results of this project on, and you can see the timeline of how the bound shifted, and it's actually quite a fascinating read. But the main bound that they got was they managed to get it down to 4,680. And they were in the process of writing up a paper, actually with a slightly weaker bound. I think they were using in the paper itself, I think 5,414 maybe. But then we got a bit of news from Oberwolfach in Germany that apparently the bound had come down again. And this really excited me at the time, because when this was happening, I was in my master's year at York. I was writing up my project very much on this area. And whilst Zhang's paper was very, very important, it wasn't exactly terribly well written. And the polymath paper that was also being written and was in the public domain, so I could read it as it was going, they were doing so many technical things to actually reduce the bound that it wasn't particularly useful for a master student to read. But then this news of this bound coming down again occurred, and I got very excited because, yes, maybe there'll be some other way of reading the same arguments that might be a little bit clearer, or just give me a different perspective. But a few weeks went by, and nothing happened. I think it was about 3 weeks, and no results, no paper was coming forth. Apparently, he got it down to, this guy, James Maynard, had got it down to less than or equal to 700. But we had no verification of this. James Maynard himself wasn't a particularly well-known mathematician at the time. He was a PhD student of Roger Heath Brown at Oxford. He's a very well-known guy now, though. But as I say, I thought that, okay, maybe a mistake had been found. But then the paper ended up getting released, and the bound was 600, and he managed to do some interesting stuff with non-consecutive primes as well. But from the 600, the polymath project got started on that because he used a different method in order to get this bound, which was a very elegant result, actually. And they brought it down, and it's currently sitting at 246, where it appears to be thoroughly stuck. We'll probably need some sort of large theoretical innovation in order to reduce it much further. There's actually a very strong conjecture called the generalized Elliott-Halberstam conjecture, which would bring that bound down to 6. But that seems so far out of our reach that it's not even funny. But so we've also got this result, which is very related. So instead of looking at consecutive primes, we're looking at non-consecutive primes. So we're looking at the distance between the nth prime and the nth plus nth prime. So for instance, we might look at, for instance, if m is, we're looking at the distance between every other prime. And we've got a rough growth rate on this. So this will look like some constant. We don't know what the constant is, and most number theorists don't actually care what the constant is. But the growth rate will be e to some multiple of m. So that actually grows pretty quickly, but we've got a nice result on that. So that's small gaps between primes. What about large gaps between primes? Well, this problem appears to be at least a little bit easier, at least for the average results. So lim sup is very much like lim int, except we're looking for the largest value that keeps showing up. And as it turns out, the largest value that keeps showing up is infinity. There is no largest value. So not only are primes infinitely often closer than we expect to each other, arbitrarily closer than we expect to each other, they're also arbitrarily further apart than we expect, which is weird. We also have sort of an explicit idea of how far away primes can be, thanks to this result from Baker, Harman, and Pintz. And that says that no matter which real number you choose, x, there will always be a prime between x and x plus x to the 0.525. Which is a bit of a weird number, but it comes actually from moderately sensible but technical things. If we assume the Riemann hypothesis, that 0.525 turns into a half plus epsilon for any real epsilon. So we don't actually save that much, even assuming usually the holy grail of conjectures for number theory. So this actually tells us how far apart primes can be. So if we set the first x to be a prime, then the next prime will always show up in the next x to the 0.525 numbers. So that's as big as gaps can be. And we've also got an idea of how small the largest gap will be. So this was proved, I think that should actually be, oh no, yeah, it was this year, sorry. So the first result like this by these people was actually in 2014, but they managed to improve it slightly this year. And again, this was originally done in two papers, one by Kevin Ford, Ben Green, Sergei Konyugin, and Terry Tao, and the second a week later by James Maynard, who started to get a bit of a reputation as for proving all these big important theorems about a week after someone else. But so they originally did a result like this separately, but this triple log here was squared, and they worked together, and they managed to get this result as it is. And it essentially says that the largest gap between consecutive primes up to x is going to be no smaller than this horrendous thing, which grows a little bit faster than log x. And log x is a lot smaller than x to the 0.525. So that's a bit of a embarrassing discrepancy. We'd want these two to get closer and closer together, but as on the Riemann hypothesis, we can't get much better than this 0.525. And I'm not even sure if we can get anything for this under the Riemann hypothesis. So it seems unlikely that in the near future we'll get any meeting of these two bounds, but you know, we can hope. Okay, so I promised talking about Polignac's generalization of the twin prime conjecture. So we're going to start by defining what it means to be a Polignac number. So we say that k is a Polignac number if there are infinitely many primes which differ by precisely k. Then the twin prime conjecture is exactly the same as saying that 2 is a Polignac number, and the results of Maynard, Polymath, and Zhang tells us that there's a Polignac number between 2 and 246. It should be relatively clear that we can never have an odd Polignac number, because if two prime numbers differ by an odd amount, then one of the primes has to be 2, because there's only one even prime number. So one of the primes has to be 2. And for instance, if we look at 7 differs from 2 by 5, 5 can never again be the distance between two prime numbers, because that would rely on there being another even prime number. So we're only looking at even numbers here. And there's one between 2 and 246. And Janos Pintz back in 2013 proved that there are infinitely many Polignac numbers. And he didn't just prove that, but he proved that a positive percentage of all numbers were Polignac numbers. So if we look up to some x, say a billion, that we can confidently say that about a% of those numbers will be Polignac numbers. We don't know which numbers they are, but we know that there's a positive probability of any number we pick being a Polignac number. And later that same year, I proved that every sequence that starts sort of D, 2D, 3D, 4D has infinitely many Polignac numbers. So if you pick any whole number you choose, then there are infinitely many multiples of that number which are Polignac numbers. But again, we don't know which they are. Let's consider this whole sequence thing a bit further. So Dirichlet, back in 1837, told us that if we have a sequence that starts at A, then goes to A plus D, then A plus 2D, and so on, where A and D have no common divisors, then they will have infinitely many prime numbers. The reason we put this condition of greatest common divisor on it is suppose that both A and D were divisible by 3. So A might be 6, D might be 9, then every single element of that sequence would be divisible by 3, which means we wouldn't get infinitely many prime numbers. So that's the only condition we put on it, and it's sort of a basic sensibleness condition. And we get sort of a dual result about 200 years later by Ben Green and Terry Tao, which says that the prime numbers contain arbitrarily long arithmetic progressions. So if you pick some number L, let's say 507, then we can start at some prime, we can jump a fixed distance D and we'll hit another prime, we can jump another fixed distance D and hit another prime, and so on 507 times. The longest such arithmetic progression we found in the primes is of length 23, but theoretically we can do it of any length we choose as long as we look at enough prime numbers. And not only did the primes contain arbitrarily long arithmetic progressions, but the Polignac numbers also contain arbitrarily long arithmetic progressions. This follows on directly from the result of Pintz on the previous slide, that a positive proportion of numbers are Polignac numbers. And this, so that's a mixture of that and a result by a famous result of Semerady. But again, this is kind of weird. So not only do we have patterns in the primes, we have patterns in the patterns of the primes. Now, in my abstract, I promised a little bit about prime races. And they're a little bit of a curiosity that we don't really know why they occur, but here we go. So let's say that pi of xqa is the number of primes up to x which are on the arithmetic progression a plus q, a plus 2q, and so on. Then we have a similar prime number theorem for these guys. And what this essentially says is that the number of primes on any sensible arithmetic progression with common difference q is about the same. So if you look for the number of primes on the arithmetic progression 1, 4, 7, 10, and on the arithmetic progression 2, 5, 8, 11, and so on, there should be about the same. But this only really holds as we get bigger and bigger and closer to infinity. And it doesn't tell us what happens on the small scales. So I've tabulated a few results here for the number of primes on the arithmetic progression 1, 5, 9, 13, 17, and so on, and on the arithmetic progression 3, 7, 11, 15, 19. And you'll notice that at every step here, the arithmetic progression that starts on 3 appears to be in the lead. There's a slight crossover at 25,000, but that only lasts for a short while. And most of the time, it seems that this arithmetic progression is in the lead, and we don't know why. And there's this result by Rubinstein and Sarnak from 94, which says that actually 99.59% of the time, the arithmetic progression starting at 3 will be ahead. if you're familiar at all with densities, this isn't the normal density that's happening, which is why this asterisk is here. It's something called the logarithmic density, but it's a... And Banks, again this year, proved that we have another interesting basis. So if we take 2 and every 100th prime after that, so starting with 2, then 547, which is the 101st prime, then 1,229, which is the 201st prime, and so on, then this will be an additive basis. And in fact, there's no special property about every 100th prime. Every nth prime should do the job. And that's, for me, that's kind of weird. Now, let's look at a thing called delicate primes. So suppose that we fix some base to work in Q. Then we'll say that a positive proportion of prime numbers, you can pick any one of their digits and you can change it to any other digit. Then that number will be a composite number. So let's, for instance, look at 13. Now we can change the 3 and 13 to a 14, and that will stop being prime. But we could also change the 3 to a 7, and that would still be prime. So 13 would not satisfy this result. But there are numbers that do, and a positive percentage will do. But the first one is 294,001. So if you take any one of these digits, say you take this 0 here, and you change it to any other digit, say 7, then this number will be composite. So 294,701 is a composite number. And in fact, a few people who work in the area think that the proportion of prime numbers which satisfy this property could be as high as 0.1%, which might sound small to you guys, but this property is something which doesn't feel like it should be satisfied by all that many numbers, but apparently it is. We have a similar idea, which hasn't been proven yet, but it's conjectured by Rickett, which says that, okay, a positive proportion of prime numbers should satisfy the property that if you permute any of their digits, then the number remains prime. So the first few numbers which satisfy that property is here. So for instance, obviously 7 satisfies this because there's only one permutation of a single digit, which is itself. But 199 also satisfies this because 199 is prime, 919 is prime, and 991 is also prime. We don't know if this sequence is even infinite. I would imagine it is, but you can see how this property might get harder to satisfy as your number gets more and more digits. Because obviously then there are more permutations, and your number nowhere can contain an even number, because then you could just slot the even number at the end and that would stop being prime. And a theorem of Maynard, which was uploaded today, in fact, well, yesterday for me, but today for you guys, says that, okay, if we have some large Q, and we take some digit A, which is between 0 and Q minus 1, so Q is going to be our base. So imagine if Q is 10, then we could let A be 0, 1, 2, 3, all the way up to 9. Then there are infinitely many primes which don't contain the digit A in their base Q expansion. So again, working base 10, which, let me reiterate, was not proved by Maynard because we need the base to be at least 2 million. But we could, for instance, forbid the digit 3 from showing up anywhere in the number. And then Maynard's theorem says that it would still contain infinitely many primes. So this is knocking out such primes as, obviously, 3, 13, 31. So it's not just looking at 3 at the end, but 3 anywhere in the digit, in the number. Okay, so that's about all of the conjectures that I want to talk about and the modern stuff. And I just want to leave you with this interesting little result here due to Kempner back in 1914. So we know that this series here, the harmonic series, we know that will never be bounded. That goes up to infinity. But if we get rid of every single number in here which contains a 9, then it will be finite. So this original sequence, this original series here is 1 plus a half plus a third plus a quarter plus a fifth plus a sixth plus a seventh plus an eighth plus a ninth plus a tenth. Here, for instance, we're knocking out the 9th. We'd also be knocking out the 19th, the 29th, all of the 1 over 90, 1 over 91, 1 over 92, and so on. And it turns out that's enough to turn this from an infinite series into a finite one. And how would we show this? Well, let's first ask how many numbers are there with L digits but don't contain the digit 9. So we've got 8 choices for the first digit, because the first digit can't be 0 and it can't be 9. So we've got a choice of the digits 1 to 8. And then every digit after that simply can't contain the digit 9. So we've got 9 choices for them. So there are 8 times 9 to the L minus 1 numbers with L digits, but they don't contain the digit 9. Now, numbers with L digits are always going to be bigger than 10 to the L minus 1, because that is the smallest such number. So this sum here, which is going from 10 to the L minus 1 up to 10 to the L minus 1, so this 1 over n is always going to be less than or equal to 10 to the minus L. 10 to the minus L minus 1, plus 1, sorry, that was a bit of a typo. So we're left with this sum here over 1, and that is simply this 8 times 9 to the L minus 1, because that's simply counting the number of digits between 10 to the L minus 1 up to 10 to the L minus 1, which don't contain a 9, which is counting all numbers with L digits, which don't contain the digit 9. So it ends up looking like this. It's bounded above by 8 times 9 over 10 to the L minus 1. Then what we do is we look at our original sum and we break it up. So we break it up by the number of digits in the numbers. So when L is 1, this will be counting all of the 1 over n, where n has 1 digit and doesn't contain the digit 9. When L is 2, this is counting all of the n which don't have 9 in it and have 2 digits in, and so on. So this is perfectly natural, and we can deal with this in a sum here. We've got a bound for that up here, which is this. Then this sum is a simple geometric series, which we have all learned, hopefully, how to sum in secondary school. And that comes out as 80. So we've shown that this sum here can't exceed 80. And in fact, the true value is no bigger than about 20.921. OK, so that's the single proof that I've got in my talk. I hope I've given you an idea of why looking at number theory, and in particular sort of patterns in primes, is interesting. Maybe even given some of you a few ideas to study in your own time. But apart from that, I think I'd just like to thank you guys for watching. I'd like to thank the organizers for inviting me. And if you've got any questions, please feel free to ask.
Does anyone have any questions? Can you come up to the microphone?
This one.
I think so.
Can you go back to that result from Maynard, the one about bases over 2 million?
That one?
Yeah. Hey, silly question. What gave him the idea to work in bases that large?
So I've not actually managed to go through the paper yet. I saw it yesterday and I was like, this seems kind of cool. But so the idea would generally be that you work in a general base, and then you see, okay, are there any conditions on my result which would force the base to be large? So usually you're going to be looking at, you'll come out with some form of bound, and this bound will only hold when Q is above some point.
Yeah.
So it wasn't so much him saying, okay, I wonder what happens when Q is bigger than 2 million, but more, I wonder what happens, and, oh, I've got this thing, but we need Q to be bigger than 2 million.
Yeah.
Does that kind of make sense?
Yeah, it does. Thanks.
other question?
Hello.
Hello.
There was one bit earlier on where you were very modest and you kind of rushed over it, but you mentioned that you'd proved a bit of the lecture you gave. It was you just sort of snuck it in at the bottom of a slide and did it quite quickly, so that we didn't linger on it at all, which was very modest of you. But I just wanted to sort of see what that bit was again, because it went by so quickly, and
Sure.
what you
Let me
thought
see.
about your name appearing in the list of people, like Dirichlet and Tau, and your name will be in there somewhere.
Oh, no, it's a very sort of small, simple result. It was, so the proof of it is about a page long. It's really not a big thing, but I thought was sort of a cute thing, and I did it whilst doing my master's. But yeah, so it's nowhere in the league of even the sort of Pint result above and the Maynard and the Tau stuff at all. But
I just wanted to say it again. Thank you.
Yep.
Any more questions? In that case, can we thank the speaker again? And I'll just end the recording and we will head to J Lounge. Okay. Thank you again.
thank you.